So my name is Uma. I'm a co-founder of Succinct. And thank you for the very nice introduction. So today I'm going to start by kind of talking about the motivation for ZK. So as we all know in this room, blockchains today are very restricted computational environments. And on-chain applications are made meaningfully worse from their extremely limited compute resources. So often smart contracts, they have to take shortcuts, rely on trusted oracles, make risky gas optimizations, and sacrifice a lot of functionality in the name of limited compute resources. So zero-knowledge proofs, as I'm sure is true for everyone in this room, are a really exciting new technology that kind of promise a solution to the scalability problems of decentralization. In the context of the EVM, with a zero-knowledge proof, a developer can take a very complex computation that might take hundreds of millions of gas. They can generate a proof for it using zero-knowledge proof's verifiable compute, and then they can use that computation on-chain for the price of 200K gas, which is the price of verifying a proof on-chain. And so in the context of EVM, at Succinct, we like to think of ZK proofs as kind of the ultimate precompile, where you can put any really complex computation in and use it for only 200K gas. And at Succinct, over the past year, since we've been founded, we've been really excited about these novel affordances of ZK, and we think that this will enable the next wave of on-chain innovation. So just to put some concrete examples out there, you have like clients, where you can have a ZK proof of consensus, and you can verify that to bridge between different domains, and not have to rely on trusted multisigs, which are often insecure and get hacked. There's also classes of applications like ZK oracles, where instead of relying on a trusted set of validators to provide some information about the state of the chain, you can instead replace it with a cryptographic proof. There's also exciting new developments in ZKML and bringing machine learning and LLMs on-chain. And then privacy, identity, and cryptography are other exciting use cases of ZK. And one really interesting thing about the field of ZK is that every year, provers are getting faster and faster, and there's a lot of novel algorithmic breakthroughs. And basically, even in the past few years, we've seen that proving time has gone down orders of magnitude, and we're just at the start of what's possible with ZK. Every year, you can stuff more computation in these verifiable proofs and get access to more compute on-chain. So at Succinct, we've spent the last year building and deploying these next generation ZK applications to production. So as they mentioned in the introduction, we're most well known for our work on ZK-like clients. We've built an Ethereum ZK-like client that helps secure the bridge from Ethereum to Gnosis chain. And more recently, we've been working with teams like Avail and Celestia on ZK-like clients for their Alt L1 DA layers and bringing that state to Ethereum. Also recently, we've been working with a bunch of teams on the ZK Oracle use case for verifying computations that don't fit in the EVM. As a concrete example, teams like Lido right now have to rely on a trusted multisig of 5 people that basically put on chain the value that's locked in all the Lido validators. However, this can be replaced with a cryptographic proof of the beacon chain balances of the Lido validators, and we're working with them and a few other ZK teams to bring the ZK Oracle to replace their trusted Oracle. And there's many such use cases that we're working on in the Oracle realm, including historical proofs at the execution layer and other validator statistic use cases with some of the other teams listed up here. One thing we've experienced at Succinct, and we know firsthand from pushing these ZK applications to production, is that developing and deploying ZK today is a total nightmare. So one of the reasons for this is that there is no mature developer tooling for ZK. If you're a developer who's doing front-end development, you have a pretty mature tech stack that makes your life really easy, but the equivalent does not exist for ZK. In ZK, circuit languages are often arcane, they lack any documentation, and you might just have to read through a bunch of scattered GitHub repos to figure out what's going on. There is no central repository for knowledge of circuit primitives or even understanding what other people are building with the same tech stack, and no examples for a new developer in the space to look at. Some more practical problems include the overhead of ZK, which is great. And so if you try to do builds and generate proofs locally, that can often be really slow. And then you have a convoluted development process where you have to SSH into a remote machine and run a bunch of stuff. And then finally, if you have multiple different builds, you have to manage this complex pipeline of verifier contracts and version circuit artifacts and witness generation. And often this is error-prone and really time-consuming. Okay, so say we've done all of that, gone through all of that pain. I hate to inform you that writing a circuit is only 20% of the work. The remaining 80% to actually take a ZK app to production that we've encountered involves a lot more infrastructure. We've had to write reliable relayer infrastructure for watching for proof requests and then relaying proofs on-chain. We've had to make sophisticated infra for on-demand scalable proof generation that scales with the load of proofs, which can be very variable. In production, liveness failures can be catastrophic, and so it requires extremely high availability. And then managing our on-chain verifier contracts across a variety of chains is also a huge pain. So at Succinct, we firsthand had issues with all of this, and we know how difficult it is to develop with ZK. But stepping back, we've also observed that the difficulty of ZK development has also shaped the ZK landscape more structurally, and that's what I'm going to talk about next. Because ZK development is so difficult, today, if you're a dApp and you want to use ZK in your application, it's generally hard for you to use ZK yourself. You usually have to rely on a specialized ZK professional. And so, as I said, most of the ZK apps today, like light clients, machine learning, storage proofs, privacy, are written by ZK experts and teams with a lot of ZK knowledge, like ourselves. And these teams have a variety of approaches. So some teams hand-roll their own custom circuits, which can be very performant, but requires a lot of developer expertise and can be cumbersome. Other teams develop SDKs and DSLs for their specific use case, which can be a little more flexible at the cost of a little less performance. And then finally, there's some teams taking an approach with ZK VMs that target different ISAs like EVM, WASM, RISC-V, etc. And those can often be very general, but come at the cost of even more reduced performance. And we think that all these approaches are valid and make sense for different contexts. So even though all these teams take different approaches, and you can observe each of those instances in the wild, one uniting theme that we observed at Succinct is that each organization in ZK today builds in a very monolithic way. What do I mean by this? If you look at a ZK team today, you might observe that they are building the following. They generally have their own proving system or heavily modify or champion existing open source proving system and build their own circuit libraries and primitives. So that, for example, in the Halo 2 stack is the Snark box. Then they'll develop their own custom infrastructure heavily tailored to their own proving stack in-house. Finally, they'll have their own smart contract layer to manage proof requests and proof verification and integration with. And then lastly, they'll build a set of utilities, such as proof explorers or relayers or things like that, all custom to their proof stack as well. And so, like this diagram shows, you might have two different teams. They might even be doing relatively similar use cases, but they've built much of the same work, just with like different specifics. And so we've observed this in the landscape today. We've observed all these monolithic siloed teams building pretty similar stuff, but ultimately very siloed. And it's this thing we kind of realized that this monolithic approach has certain structural weaknesses. So one thing we observed is that when you build monolithically, the dApp developer, who is the end user of ZK, has a lot of problems. And so one of the problems they face is the problem of vendor lock-in. So in a monolithic world, there's no shared APIs or standards, right? Because all the teams are siloed and generally building their own bespoke infrastructure and integration pipeline and stack. And so if you're an application developer trying to use ZK in your app, you often have to learn custom tooling or integrate bespoke solutions. And if you want to migrate between different stacks, if you're unhappy with one for whatever reason, it requires a lot of effort because nothing is standardized. And this increases the barrier to entry for ZK adoption and imposes vendor lock-in because of high switching costs. Furthermore, we observed this personally, that in the monolithic landscape, there's a lot less flexibility and increased coordination overhead. So oftentimes we've collaborated with teams and they've wanted certain small changes to the circuits we've made for their particular application or use case. And often in the current status quo, they have to contact us through Telegram or Slack and tell us what changes we need to make. This is fundamentally pretty unsustainable because it comes with a really high coordination overhead, and often there's no guarantee that the ZK professional you're using will make the changes that you need. And then finally, the most interesting point is that the ZK space is rapidly evolving. As I mentioned in the beginning, the proving times have gone down orders of magnitude every year. There's novel algorithmic breakthroughs on the research side. There's novel engineering efforts on the more industry side. And so those two things combined mean that there's a really fast evolution of proving systems and stacks. And that means that the optimal stack that you might want to use for your use case will change. Furthermore, different computational workloads often require different proving system optimizations. So for certain use cases that are really sensitive to latency, maybe having a really custom-tailored handwritten circuit makes sense. Maybe for other use cases, a ZK VM is good enough. In a monolithic landscape, because there's really high switching costs and vendor lock-in, application teams are at risk of using previous generation technology if their monolithic stack cannot adapt to the latest technology as it comes out. So overall, it's distinct. We observed that this monolithic architecture that dominates ZK today is slowing down adoption, making ZK developers' lives harder, and is not sustainable. And we think that there's a different way. So over the past few months, we've kind of observed the landscape, we've observed our own challenges, and we've articulated this vision for the future of ZK development that is kind of a counter thesis to the monolithic architecture that I just outlined. So in our vision for the future of ZK, we think that there should be shared APIs and standards that are critical for reducing friction for ZK adoption. So in particular, if you're a developer, ideally, you can just switch between different implementations of proofs for your use case with one parameter change in your contracts. And this will result in minimal vendor lock-in. Furthermore, as I mentioned previously, the ZK space has all these novel algorithmic breakthroughs, and prover efficiency is dramatically improving by orders of magnitude every year. We think in our vision of the future of ZK, developers should be able to modularly switch to the latest technology as research and engineering advances. And then finally, we believe that there will never be one proof system to rule them all. ZK VMs might be good for certain use cases, circuits might be good for others, SDKs and DSLs for a third category. And we think that a diversity of proof systems will reflect a diversity of use cases. A really concrete example is that a team from Stanford was able to deliver 1,000x speedup over a naive ZK approach for ZKML. And we think that this pattern will continue throughout the wide variety of use cases that persist. And so we think that all developers should benefit from shared tooling that will be proof system agnostic and be able to accommodate all these different proof systems that will persist in the future. So that vision was kind of like our high-level goals, and it's like more vague. But it's this thing we've been thinking about, how can we create a new architecture for ZK development and deployment that enables this vision? And that's what I'm going to talk about next. So I want to introduce the succinct protocol, which is kind of an open infrastructure layer that helps realize this vision. So what is this succinct protocol? It's just a simple set of several minimally opinionated standards and proving system agnostic components built from the ground up to be more modular and kind of realize the core theses of our vision and help solve the problems with the monolithic architectures of today. So more specifically, there's kind of three components that we have right now that I'll go into talking about. So the first component is a proof standard. The proof standard gives dApp developers a unified interface to request and consume any ZK proof within the EVM. So remember, one of our core theses of kind of our vision was that dApp developers should be able to modularly switch between a bunch of different implementations, no matter the proving system, and this lets them use the best technology as it comes out. And so you can see here, the proof standards in the center of the diagram, and all the surrounding boxes come from different proof systems, they come from different VMs, and they're doing different functions as well. Okay, so more concretely, if you're a dApp developer, the heart of the proof standard is a succinct gateway contract. The succinct gateway contract is a very minimally opinionated ERC-like contract where you can request proofs on any chain. You just put in a function ID and you put in your input bytes, and it goes into the gateway, which emits an event. Then we generate a proof off-chain, and then after the proof is generated, we verify it through the gateway, and after the proof gets verified, your application has access to these verified outputs. The gateway is really nice because it simplifies developer integration with any proof system through this standardized interface. So if you're a dApp developer, you only have to worry about the gateway address on any chain, which is a single address, and you have a standardized template to talk to any proof system or any verifiable compute. And if you're a proof system, one thing that we found from our personal experience is really tricky is the inputs and outputs between on-chain inputs and how the proof system represents the same variables in field elements. So if you're a proof system, our proof standard is just a simple spec where any proof system, as long as it standardizes its public inputs to adhere to the simple specification, it can be accessed through our gateway. So if you're a proof system, you can integrate with the standard, which is quite simple. And we've done this today for a few existing proof systems like Polkey2, Gnark, and CircCom. And it's really easy to integrate new proof systems into the standard. It's very lightweight, so you could have ZK VMs integrated into the standard. You could have SDKs and DSLs integrated into the standard. And if you're a proof system and you integrate with the standard, you can expand your distribution because now it makes it really easy for any application developer to use your stack through the gateway. The next component after the proof standard is a proof marketplace. As I mentioned, with the proof standard, it provides this unified interface to request for proofs from any proving system. During proof generation, today with Succinct, we just generate the proofs for you, so it's nice and simple. But in the future, we think that dApps will require competitively priced, highly available, decentralized proving. So in the future, we imagine that the best solution for this problem is an open proof marketplace where any prover can join and earn fees for providing their compute. And the open marketplace will foster competition for cost-effective hardware and make the price of a proof as cheap as possible for the application. And then finally, the last piece of the Succinct protocol that we think is critical, and this should say proof aggregator instead of proof marketplace, is a proving system agnostic aggregator. So today, for some context, if you want to verify a proof on-chain, it costs at least 200K gas. With the proof standard, because now all these proof systems have standardized their inputs and outputs, we can now leverage that standardization to build an aggregator that aggregates proofs from a variety of different proof systems. With ZK, because you can do this additional level of recursion and aggregation, instead of having every proof verified for 200K gas, you can drive the cost of verifying a proof to zero. And this will help enable the next 1,000 ZK applications because now the cost of a proof and verifiable compute is even cheaper on-chain. So I've kind of talked about the high-level overview of the Succinct protocol and all the different components we think are necessary to build to make ZK development and deployment more modular and coordinated. And today, the proof standard is live. We have a gateway contract deployed on a bunch of chains, and we have a bunch of different proof systems, as I mentioned, integrated into the standard. The proof marketplace and aggregator are things that are more futuristic, and we anticipate building in the future. But if you're a developer and you want to start building with the proof standard and actually building ZK applications today, the easiest way is to do this through the Succinct platform. So you can think of the Succinct platform as kind of a front end for the Succinct protocol and the easiest way to start building with the power of the Succinct protocol. And the architecture of the Succinct platform is uniquely enabled by the protocol, and it's built with a lot of the same vision in mind of modular adoption of the ZK stack. And the platform is live today at alpha.succinct.xyz, and here's a screenshot of what it kind of looks like. So I'll walk through how the platform kind of interacts with the protocol. So what does the platform actually let you do? So if you're a developer and you go to the platform today, the first thing you can do is the Succinct platform provides you with a central location where you can discover what ZK applications are being built, and you can learn more about the latest advances and use cases of ZK tech. So in particular, we have this nice feed of all the projects, and we have a list of trending projects sorted by stars, and you can see what's going on in the ZK world. We think this is a huge missing piece of the ZK community, and we think the platform hopefully makes it more legible for people to understand what's even possible to do with ZK. Next, after you've gotten inspired and you want to start building with ZK, we have a lot of tooling in the platform that's fundamentally proof system agnostic. And you can use all of that shared tooling to start quickly iterating and developing with ZK. And I'll go over a list of those features in the next slide. And then finally, once you're done developing, then we have a one-click deployment workflow and reliable infrastructure to help you use your ZK app in a production setting and be confident about its usage and reliability. So, as I mentioned, our platform is built with the same vision as our protocol. It's meant to be modular, it's meant to be proof system agnostic, and it's meant to provide these shared utilities and tooling for any proving stack to make ZK developers' lives better. And so, more concretely, some of the utilities look like you can connect your ZK project with GitHub, and we have a nice organization and collaboration features. We have circuit builds in the cloud that are really fast, and we have versioned artifact management, so you never have to SSH into a big machine again to do your builds and manually copy-paste verifier contracts. We have a one-click deployment workflow of verifiers to any chain, and we use the Succinct gateway for integration, so it's really easy now for your application to integrate with the stuff you build on the platform. Finally, we have production-grade managed relayer infrastructure and auto-scaling API endpoints that fulfill the proof generation now. And in the future, this part will be taken care of by the proof marketplace in the Succinct protocol. And then as I mentioned before, the sharing and discovery experience we think is really important. And so once you've done all this and you're using your ZK application in production, you can share your project with the ZK community and you can get featured as a trending project on the homepage. So we think that in combination with the philosophy of our protocol and then the practical utility of our platform, that the future of ZK development looks a lot better than the monolithic standards of today. So if you're a ZK developer using the Succinct platform, you are able to use our unified tooling and workflows, and you can use any proof system that you want as long as it conforms to the simple specification and standard, and you get this really nice developer experience for any proving stack. And again, because we support any proof system, if there's some new technology that comes out that is better for your use case, you can modularly switch to that technology. And finally, as I mentioned, all the utilities and tooling in the platform that I just discussed are built in this coordinated, pre-system agnostic manner so that all ZK teams can benefit from shared infrastructure. So instead of having these monolithic siloed teams building all this duplicate infrastructure, there's one place where now every ZK team can tap into this layer that just provides them the infrastructure to make everyone's lives better. And we hope that the Succinct protocol's architecture and the platform's developer tooling altogether helps accelerate ZK adoption. So we've built this all out. It's working. We've been using it internally for a few months, and we've been also using it with some external teams. So if you go to alpha.succinct.xyz/discover today, you can discover what teams are using Succinct. We have some bridge implementations, like I mentioned, with Celestia and Avail. And then we have some Oracle implementations like Nouns and EigenLayer that are using us. We have a Tendermint-like client. And there's a bunch of other projects that you can see how they're using ZK and how they're using the Succinct gateway and tapping into kind of this shared infrastructure. So at Succinct, we're really bullish ZK. We think it's the future of solving the scalability problems of blockchain. And we think we're only at the tip of the iceberg in building new applications on Ethereum. So identity, on-chain machine learning, Oracle's like clients, that's just the start. There's a lot more to be built. And so if you're a dApp developer and you're really interested in building with ZK, please reach out to us. We would love to have you build with Succinct. And if you're a proof system expert developing the next generation ZK technology that's going to power all this stuff, we'd love to have you integrate into this modular ZK stack and make it easier for the open source community to build with your tooling. So yeah, feel free to reach out to us at that link, and we'd love to chat. That's all. Thank you, guys.
Thank you very much. Do we have any questions? Question over there. Thanks. Is on? I'm wondering if you could comment on, are you seeing a heavy audit burden on ZK circuits? And I guess I'll load the question a little bit by wondering if there's eventually an opportunity to have like an open Zeppelin type of canonical set of circuits that are widely enough used that you can share the audit burden.
Yeah, we've definitely seen that auditing is a tricky part with ZK. We also, I didn't kind of mention this in this presentation, but we have some of these open source libraries that we use in developing a lot of these projects that we're getting audited, and will kind of form our circuit primitive base. And the hope of the platform is like, you can go to Discover and you can see like the audited tag and see like, oh, these are primitives that are audited that other people are using. I should use them too.
Yeah, I wanted to ask, are you looking maybe into ways on how to maybe shield the inputs? Because so how I understand in your live clients, you're actually disclosing basically the proof arguments, or you're just like outsourcing that. So for privacy use cases, for example, that would be, for me at least, for from a privacy engineer perspective, like a no-go, so to say. So how are you looking into maybe creating something more secure into how to offload the proving generation?
Yes, I think the question was around like kind of how can you build privacy preserving applications using the platform. So today, most of the applications we have are just focused on scalability. But if you want, like, they do have some private inputs, and there's like methods of doing that in our SDK. But since all the proof generation is hosted, for true private applications, you need the proof generation to be done client side. We have some idea, like the development process around like managed circuit builds and like witness generation and like verifier contracts can still be useful for privacy-based applications, if that makes sense. So a lot of the tooling, for example, the Proof Explorer is still useful for a privacy application. I think we'd have to figure out basically how you could use like those binaries on the platform and then have that generated client side. But I don't think there's like any fundamental barrier to having that work.
Question at the front.
So it seems like, if I understood correctly, the request and response for the proof is on-chain. Do you guys have a flavor of this that serves the off-chain proof use case? So I want to request a proof. I'm only going to use it off-chain, so I want to do the whole,
Yeah, we do. So I only talked about the on-chain request response flow, but we actually have an API where you can request a proof off-chain and then you can just get the proof back. Or you can request the proof on-chain and then have it call a callback on-chain. So you can do off-chain requests with an on-chain callback too.
Any more questions? Oh, we do. Sean, behind you. Behind you.
So what is the pricing model when you're requesting a proof?
Yeah, so right now, like we just do hosted proof generation. So it's kind of like, I don't know, when you use Alchemy, you have RPC credits. It's similar to that, like proof credits or succinct credits. In the future, I think the decentralized proving marketplace will kind of take care of the pricing because it'll be this like open marketplace with competition. And that will just provide the most competitively priced stuff.
Amazing. Thank you very much. Round of applause.